Glad you're here for the first lecture on complex variables and analysis. And today we are going to study some historical background, geometric point of view, represent and some representation of complex number in various coordinate systems, and then we will do some operations on complex numbers. So first of all, the historical background. So let's say what was there when the complex number was not invented or discovered. So mathematician was doing good with the real number system. That means there are several number sets. We can call this a real number system. After appending all this in a set or in a single set, we can call this a real number system. Let's say the natural number system, that is n. N is a set of all natural numbers, that is all countable numbers are grouped here. And then we can call it the Z, that is the set of all integer numbers. So in this set, we are considering all the numbers that are positive whole numbers, negative whole numbers, and obviously the neutral number 0. So basically, in this set, we are considering minus infinity to minus 3, minus 2, minus 1, 0, 1, 2, 3, and up to infinity. So this set is basically the set of all whole numbers, positive, negative, and obviously 0. And then there are rational numbers Q. Rational numbers are those numbers which we can represent as a ratio of two integer numbers. So if x is a rational number, then x can be represented in the form p by q, where p is an integer and q is also an integer. And obviously, q is not going to be 0 because something divided by 0 is undefined and it's not making any sense. So obviously, Q, the set of rational number, is all those numbers which we can represent using the ratio of two integer numbers. And there another number Q prime, or someone just might represent it as QC. But okay, so this number is called the set of all irrational numbers. So irrational number are those numbers which we can represent in the ratio of two integer numbers. Let's say P and Q. So not in the form P by Q, and obviously Q is not equal to 0. So this type of problem arises when scientists or mathematicians are basically trying to solve this type of equation: x squared minus 11 is equal to 0. So let's say this is a real world problem and it arises in some cases of the real world. Then we may find that x is equal to root over root over 11. So we can't represent this number using our natural number system, integer number system, and obviously not in the rational number system. So as we don't group it as a rational numbers, so there are some numbers other than rational number, and to solve these numbers, we introduce the irrational number set. So the most common irrational numbers are pi, e, and so on. So now, if we just combine the rational number set with the irrational number set, we get our real number system. That is, our real number system is basically Q union Q prime. That means if we just take the union of these two sets, then we got our real number system. So after invention of the real number system, mathematicians are doing good, and they almost believe that there are no such solution of such kind of equation: x squared plus 1 is equal to 0. Some book already described that mathematician invented the complex number I, or imaginary number a plus ib, while trying to solve this equation. But it was not true, because back then many mathematicians believed that if a real problem has if a real problem involved a square root of negative numbers, then those problems are quite unsolvable, and they just discarded the solution. And it was not the quadratic equation, because the general solution of a quadratic equation x squared plus bx plus c is equal to 0 was discovered many years ago by x is equal to minus b plus minus root over b square minus 4ac divided by twice a. So, well, if they got something here that is weird, like root over minus something, then they just discarded the solution, saying that this problem is not solvable in the real world. So, after that, they many mathematicians already tried to solve the general version of the cubic equation, that is this one, but mm, they failed many times because uh, in fact some prominent mathematicians believe that the solution of this equation is impossible, or the general solution of this equation is impossible, because obviously here there's something weird going to happen, so we can say that this is not possible. So after that, after trying for years, a mathematician called Del Ferro first attempted to solve the depressed version of a cubic equation, and the depressed version is basically x cubed plus bx plus q is equal to 0. So this is a depressed version of the cubic equation where the x squared term is uh, not there. So he just found the solution of this type of equation as, if I just add a picture of it, then it will be something like, okay, so this one. So I believed, okay, just a minute. So this is the solution of the depressed cubic equation mentioned above. So in this equation, he just solved the general version without the x squared term. So here he is doing good, but he kept his problem or his invention secretly. So Delfero's solution was not uh, published in that time. Then a few years later, Tartaglia also found the solution of a different version of the cubic equation as follows, and then he also kept it secret because they didn't want to publish their invention, and they didn't want others to know about their solution, because if the cubic equation is you know solvable, then you can, or many person can solve a variety of problem, and variety of real world problem has some answers of it. So yeah, and then later Cardano came up with the idea to solve the general version of the cubic equation, ax square x cube plus bx square plus cx plus d is equal to 0, and the general version was mentioned as, if I just add the picture here, so this is the general version of the cubic equation. But the thing is, here is here a weird number appear. So weird number is basically plus root over 3i, and the second one is minus root over 3i. So Cardano basically described this problem as subtle, as useless, and this he basically discarded these numbers and only focused on the real one he got. So he got the real one and said that the other two is basically useless. Later, the official calculation with the complex numbers began when Bombelli started up with the idea to solve this equation. So we can solve it using our depressed version of the cubic equation, but there is a problem. It is a real world problem. But if we just focus on the solution, or if we just consider an intuitive view of the solution, we can find that the solution of this equation is x is equal to 4. So this is also a real solution. So, but what is the problem here? Because if we just consider this equation as x cube plus px plus q is equal to 0 and try to solve it using our depressed version solution, then we get something like cubic root of 3 2 plus root over 4 minus 1 to 5 plus cubic root of 3 2 minus root over 4 minus 1 to 5. So we are just substituting the values of p and q's and then we are getting this result. So after simplifying this a bit, we get 2 plus root over minus 1 to 1 plus cubic root of 2 minus root over 1. Sorry, this should be minus 1. So, but we got some weird number, let's say root over minus 1 to 1 in both cases. But the thing is, our solution is a real solution. That means we can do operation on these weird numbers. So Bombelli basically came up with the idea that let's consider root over minus 1 is equal to I. So Bombelli basically came up with the idea that okay, so if this number is root over square root of some negative numbers, we can consider it as x is equal to 2 plus n times I. N is any number, and then 2 minus n times I. So 2 plus ni is basically the solution of this part, and 2 minus 3i is basically the solution of this part. So then he just cancel out this imaginary part or weird part, and then finally got the solution as 2 plus 2 is equal to 4. This is a bit weird because uh, for that we need the concept of two things. That means uh, if a complex number is something like this, that means we are considering the summation of these two complex number as a plus c plus I times b plus d. And again, there are some other calculations needed because we are considering 2 plus ni as 2 plus ni as the cubic root of 2 plus 11i. That means if we just powered the value to 3, then we will get 2 plus ni to the power 3 and then 2 plus 11i. So that means we need the multiplication rule too. So this is our addition rule. Sorry for this. This is our addition rule and we need the multiplication rule too. Our multiplication rule will be something like a plus ib and then times c plus id. So what is happening here? AC minus bd plus I times AD plus BC. So here, as we consider I is equal to root over minus 1, we are considering I square is equal to minus 1. So after considering this equation is basically became. So later, after some calculation, it was valid that 2 plus minus I whole cube is basically 2 plus minus 11I. So this is where the first substantial calculation of complex number just began, and after that it's just many mathematician invented many things, but the main history came from this part, that is where the complex number made its first run into the real world. Later, what can we think? So what is a complex number? So we are just going to consider the geometrical point of view. So geometrically, what does that mean? Geometrically, a complex number is an invisible identity and a single invisible identity in a plane, because yeah, obviously with a real line, that is a real number system is considered by a real line from minus infinity to infinity. Using our real line, we can't represent our uh, complex number system, because our complex number system z is equal to x plus iy has some extra dimension here. So we just represent it as a invisible identity in the plane. So this identity will be something like, let's say z, this is our point, so this is our point, z is equal to x plus iy, and this will be something like, if we just add it a bit, then this is our y and this is our x. And then the thing is, there are 2 points. As we are considering our complex number as a single quantity in a plane, and we are just representing it as, we can represent it represent a number in a two-dimensional coordinate system, so we can use our vector rule. So if a is a complex number and if b is a complex number, then their result, that is their summation, will obviously follow the parallelogram parallelogram rule. That is obviously. And then a times b will follow the a complex number has some length and magnitude, some magnitude, so their product will be the products of their length and the angles angle will be the sum of things. So if you're considering this in the Cartesian coordinate system and two-dimensional coordinate system, then you can say that it will obviously follow the parallelogram rule for summation, and obviously a times b will be the product of their length and the angle. This angle will be measured from the positive x-axis. So if this is a complex number z, then its angle theta is basically the angle from the positive real axis. So now we'll just look at some properties of complex numbers. So let's z is a complex number. So this is z. Z is a complex number x plus iy. So its real part is represented by re of z. That is the real part of z. We are just getting introduced to some notations in complex number, and then the imaginary part of z will be Im of z. And then finally, we will consider the conjugate, that means z bar. So this is basically the mirror reflection of a number. That is, if a number is in the first quadrant, then it will be replaced to the fourth quadrant, reflection with respect to the real axis. So z bar is basically the conjugate of z. So if z is equal to uh, x plus iy, then it is basically, as we are considering z bar as the mirror reflection, so this should be x minus iy. So this is representing the conjugate of z. And then finally, modulus of z. So what is the modulus of z? Modulus is basically the distance between the complex number in a plane from the origin. So if we are just considering this, the modulus of z, then we can say that this should be root over x square plus y square. So we can just use the Pythagoras theorem here to find the modulus of z. and then this is x square root over x square plus y square. And then as we are considering the complex number as a quantity here, it has a length, and this length is basically the modulus, so this one, and we need an argument that is theta. So the argument of a complex number will be represented by arg of z, and this is basically the angles from the positive real axis. So obviously, as we can find the argument, that is our theta. So this is our theta and the modulus, and this is our r. So we can represent the complex number system in Cartesian coordinate system. So in polar coordinate system actually, because z plus x plus iy. So this is in the Cartesian coordinate system, and if we just move to a bit further with r and theta, then this is the representation in polar coordinate system. So this is the representation in polar coordinate system. So what do you we are just considering the representation as r angle theta, but we'll use a very convenient notation later. But up to now, we are just considering the polar form as a r angle theta. So we already know about that. This x is equal to r cos theta. We are just taking the component. That means if this value is r, and then if we are just taking a perpendicular line from the point z to the real axis, then this is our r cos theta, and this is r sine theta. And obviously, we already discussed about that r is equal to x square plus y square, that is modulus of z, and theta is equal to tan inverse y by x, and this is our argument of z. Obviously this will vary from quadrant to quadrant. If it's the first quadrant, then the value will be just considering a bit, the argument will be something like, let's say, finding the principal argument here. So if we're just considering the coordinate system as this, and we are trying to find the principal arguments from this, we get, let's say our point z is in the first quadrant. Z is in the first quadrant, x plus I, y. And we are defining an angle alpha is equal to tan inverse modulus of y by x. So what is our principal argument? Principal argument means, that means if we are considering our argument, the principal argument, if our argument is confined between the angles minus pi to arc of z pi. So what's the point here? And why we are just considering this range for the principal argument? Okay, so why we are considering this length for the principal argument? Because, you know, if we are considering a complex number, let's say this is a complex number, it has an angle theta. So if we add another twice pi angle to it, we get the same theta. If we get another twice pi angle to it, then we will get exactly same theta. So from here, before finding the principal argument, we can say that r theta is equal to r theta plus twice pi plus r theta plus 4 pi, and so on. Obviously, if we just considering the clockwise rotation of these angles, that means as we are adding 2s pi means we are following the counterclockwise rotation, but if we just follow the clockwise rotation, then we'll also get the same angle, that is r theta should be r theta minus 2s pi is equal to r theta minus 4 pi, and all these angles are exactly the same. So there are infinite numbers of angles there, because if we just add or subtract any multiple of twice pi, then we'll get the same angle here. So we are just going to find out the principal argument, that means the angle which is confined between the minus pi and pi. So what will happen? So let's say our first complex number is in the first quadrant. Then if we just add it a bit, and then take a perpendicular line from here, this is our x and this is our y, and this is our theta. That is the argument. So obviously our principal argument will be theta is equal to alpha, because we are in the first quadrant and all the quantities are basically positive, so taking more or less is exactly same as not taking it here. So for the second quadrant, let's say our point is basically this one. So after adding it a bit, this length is y, length is not negative. I am just talking about the length. So this length is y and this length is x, and the length is basically the negative x-axis. So what is happening here? So if we are just going to find out this alpha will be this angle, but we are not considering this angle as our argument of z, because argument of z is basically the angles that is considered with the positive real axis. That is, this is our angle which will be considered. So in the second quadrant, our angle will be theta is equal to pi, because this is the pi angle, minus alpha. So this is our another principal argument. So this is the principal argument for first quadrant, and this is the principal argument for the second quadrant. So let's say in the third quadrant, our point is in the third quadrant. So this length is x, this length is y, and all the coordinates are basically negative, and this is our point z equal to x plus iy. So if we just and this is our angle alpha, and if we just say we will find our principal argument as pi plus alpha, this is basically going out of the range. So we can say that this is our this angle will be pi plus alpha. So this should be, we'll move from the clockwise direction from this point. So this should be theta should be minus pi, and then in the counterclockwise direction from up to alpha. So this will be something like, our principal argument will be theta is equal to minus pi plus alpha, and obviously you may already know about it. I think if a point is in the fourth quadrant, then will the principal argument will be, this is our alpha, so our principal argument will be minus alpha. So we can find the principal argument within using this form. And then now geometrically, what is means by multiplication? Let's say I am saying, sorry, let's say I am considering the multiplication of two complex numbers. Let's say z is any complex number and we are multiplying it with a number a is equal to 4 plus 3i. Then what will happen? So az is equal to 4 plus twice I z, and then 4 z plus 3 I z. So what will happen if we just multiply a number with a I, complex number AI, and complex number obviously is a more general form. It can be a real number, it can be a complex number, anything, because complex number is the superset of a real number set. So yeah, if we just consider the imaginary part as zero, then we will get the complex number system. So from here we get, so at first we need to understand what it meant if we just multiply a complex number by I. So let's move forward. We just consider what is happening if 2, a scalar, is multiplied by a -1 or a negative number. Then we get minus 2. And if we again multiply this by minus, then we'll get 2. So in total, a 360-degree rotation in the real axis. That means if we are just considering this as 2, then multiplying by -2 will happen, leads to 180-degree rotation. And what will happen if we just consider a 90-degree rotation? Sorry, what will happen if we just consider multiplicating by I? Let's say 2 is a number. We just want to multiply it with I, and then we'll get twice I. And then again multiplication by I will have 2i square, and 2i square is basically -2. So that means after multiplying 2 times by I will get -2. That means after multiplication by I 2 times, we get 180-degree rotation. So what is I doing here? I is doing 90-degree rotation here. So obviously as I is doing 90-degree rotation here, all the numbers in this axis, that is the perpendicular to real axis, is basically the purely imaginary numbers. Okay. So from here, now we can say that this is 4z plus 3 times z rotated by pi by 2 or 90 degrees. So just let's draw a picture of this. Let's say this is our z point. Let's say this is our z point. So what is happening here? Z will be multiplied by 4 times. So this will be again and again and again. Just so this is z, this is z, this is z, this is z, and this is z. So we get our 4z. This is real axis, and this is our imaginary axis. And then we consider a 90-degree rotation. That means Iz. So 3 times z rotated by 90 degrees. That means, so this is Iz, this is Iz, and this is Iz. So obviously our A times Z is basically this number, this complex number. So how can we say that what will be the length, and obviously what will be the magnitude? So our initial complex number was A is equal to 4 plus 3i. So if we just take the modulus of A, then we'll get root over 4 square plus 3 square. That means 16 plus 9, so root over 25 is equal to 5. So what is happening here? Because we are just want to consider the modulus of A times Z. So the modulus of A times Z is basically here. Z is multiplied by 4 times. So this length will be 4 modulus of Z, and this length will be 3 modulus of Z. Okay, so we are considering the length only, and square, square, root over. So eventually, what we got? We got 5 per modulus of Z. And again, what will be the angle of this? Let's say this length is Z has an initial angle, and this angle is theta, and it is moved to another angle. We are just going to find out what is this angle. So let's say the first angle is okay. So here the angle of A will be tan inverse 3 by 4. And basically, after multiplication by A, we are getting that this angle is moved to a, this is our angle, tan inverse 3 by 4. So we will actually consider it when, or we will give the visual representation of this angle rotation in the polar coordinate system when we will study the rigorous form of the polar coordinate system and also the Euler equation, because before introducing the Euler equation I didn't want to consider e to the power I theta. That's why I am just keeping it secret. So yeah, after I introduce the Euler equation, then it is very easy to, it will be very easy to visualize that multiplication by a complex number is obviously rotation of is rotated by the angle of those number. So what you can say? So geometrically, multiplication by A is equal to R phi is the rotation of the axis by angle phi, and expansion of the plane by r, because this 5 is the modulus of A. So if we just multiply this by 5, then we get our actual. Okay, so multiplication, geometric multiplication by a complex number is just basically doing the expanding the length by the modulus of that number, and the angle will be added to the initial angle of z. So what are the basic operations for a complex number? So basic operations. The first one is the addition. That is, if we just add two complex number, then they will follow the vector rule, because we are considering the complex number as a single invisible quantity in the plane, so we can consider it as a vector. So they obviously follow the vector rule, and then by the vector rule we can say that A plus C plus I times B plus D. and then a plus ib. If we are just considering the subtraction, id will be a minus c. So c plus id, this should be a minus c plus I times b minus. And then if we just multiply these two numbers, c plus it, then what do we get? AC minus BD plus obviously AD plus BC. Here we are considering I square is equal to minus 1. And then if we just divide A plus IB by C plus ID, then obviously C and D are both simultaneously not 0, because if they are both 0 at the same time, we'll get 0 in the denominator, and this is not making any sense. So yeah, so if we just our first goal is to uh, remove this I from the denominator, because we just want to represent it as the form x plus iy, that means real part plus I times imaginary part. So for that reason, this should be c plus id times c minus id, and then a plus ib times c minus id. So this should be a c plus bd bc minus a d. So this should be plus, and then c square plus d square. So from this case we get ac plus bd, and then c square plus d square plus I times bc minus ad c square plus d. Okay. So this is the basic representation of this number, and gen, and these are the basic operations for a complex number. So the last part, we can represent any complex number in a matrix form. So if a plus ib is a complex number, so then its matrix form is a minus b, b, a. So this is just a matrix representation, and we can verify that this matrix representation also hold all these operations defined above. Let's say 2 plus 3i is multiplied by 4 minus I. Then from our conventional way, we get 4 plus 12i minus twice I minus 3i squared. So this will be plus this. So 7 plus 10i. Then if we just consider the matrix multiplication, in that case, 2 plus 3i, this should be 2, 2 minus 3, 3. And then 4 minus I, 4, 4, and then 1 minus 1. And if we multiply this matrix, then 4 and then 7, 2 minus 12, that is minus 10, and 12, 10, and then 3, 7. So obviously this is 7 plus 10 I. So we are getting the same answers here as well. If we just consider a division by two numbers, 2 plus I by 2 minus I, and in case of division, we just consider it as, so in case of division, we are going to just do our natural result, that is 2 plus I whole square, 2 minus I times 2 plus I, and then we get from here 3 plus 4i, and in the denominator as 5. So if we just simplify it, 3 by 5 plus 4 by 5i. And then if we just multiply 2 minus 1, 1, and 2 with the inverse of, that is, as in the matrix multiplication, that it is defined as the inverse of the matrix, because division by two matrix is not It's not a valid operation. So yes, we can multiply a matrix, or you can multiply it with the inverse of the matrix. So this should be mm, 2, 1, minus 1, 2, and inverse, and then we'll also get the same values, that is 3 by 5 minus 4 by 5, 4 by 5, and obviously 3 by 5. So this is also 3 by 5 plus 4 by 5 I. So this is the metric notation we are going to use later for our later part. So that's all for today. So in the next part, we are going to study the Euler equation and the Moivre equation, and also the application of Euler equation in many cases. Thank you.